Can everyone hear? All set? Okay, great. So today I'll be talking about a tour of modern LLMs. And basically, the idea here is that there's many large language models available nowadays, but I wanted to go through some of the ones that are particularly interesting for various reasons, either because they disclose a lot of information about exactly how they were trained, so we can get an idea about what is involved in training a kind of state-of-the-art large language model, or because they're kind of the strongest models that you can download and use on your own, like the best open weights language models that are available, or because they're specialized to some particular topic, or because they're the best closed language models. But I'm going to particularly focus on the first two, just so like everybody has an idea about what is going into all the models that you're using for whatever tasks that you're trying to solve. So one important thing is what makes a model. So we talk about, like LLaMa 2 or Mistral or Mixtral or whatever else. And I think you know this already, but it's worth reiterating again here because I'm going to talk about it a lot today. But it's basically the model architecture. So what architecture do you decide to use? What data do you decide to use? And what training algorithm or training method do you decide to use? And all of these are important. And there was actually a Twitter thread with Tom Wolfe, who's, I guess, the CSO or CTO or something like that at Hugging Face. And basically what he was saying is a lot of people don't realize that the data is actually one of the most important parts. And the architectures are a lot less important nowadays. And I think that there's some truth to that. There's also some, a counter argument to that. The truth to that, which you'll see today, is that almost all of the models that we're using use very similar architectures. Like almost all of the models use an architecture that's very similar to LLaMa. But despite the fact that they use very similar architectures, their accuracy is vastly different, or their abilities are vastly different. So that must come from the data or the training decisions, right? So that's an argument for the fact that architecture decisions are a lot less important. My counter argument to that is we spent 9 to 10 years fine-tuning and finding the LLaMa architecture. So now we have the LLaMa architecture, which is a really good architecture. It works really well when training very large models on lots of data. And so now we don't need to use another architecture because the architecture we're using is good. But if we were trying to do the same thing with the like LSTM from 2014, then none of the stuff we're doing today would work. So that's an argument in favor of architectures being important. Also, architectures can make things faster, and that's included in some of the decisions that people use. So the first thing I'd like to talk about before I get into any of the actual details is open versus closed access. This is not like modeling stuff, but I think it's important and also helps you understand the environment a little bit. So there's a nice blog by Percy Liang and others which is also in the reference. And they discuss several different varieties of like openness of release of language models in advanced AI systems. And there are some things that we can talk about. We can talk about the weights being open, described or closed, inference code being open, or inference methods being described or it being fully closed, training being open, described, or closed, and data being open, described, or closed. And in general, we have like the open weights models that are on Hugging Face. That might just mean the weights are open. The inference code also needs to be open because otherwise you can't do inference on them if they're on Hugging Face. But that doesn't mean that the training code is open. It also doesn't mean that the data is open. And so there's various degrees of openness. And then, of course, there are things like GPT-4 or GPT models where basically all of this is closed and we don't know anything about it or know very little about it. Another thing is about licenses and permissiveness. And this is kind of important if you want to do a research project to know, because it means it has an impact on the things that you legally can do or can't do. In universities, I mean, we should be following the law, but maybe people think about this a little bit less. If you're in a big company, this is something that becomes really important. So it's important to think about. So I'm going to go through several degrees of licenses that if you've done anything in open source, you probably know. But you probably know a lot of these. The first one is public domain or CC0. And this basically means you can do anything with it. Like I could download it, and this includes the download it and redistribute it, not give you any credit, modify it in any way I want. And this includes things like old copyrighted works and products of the US government workers. So if you work for the US government in some capacities, anything you generate becomes public domain. So old copyrighted works, how old do you think they need to be before they become uncopyrighted? Yeah. I think that's pretty close. So it's 70 years, I guess. Oh, sorry. The life of the author plus an additional 70 years. So like after the person has passed away, 70 years, I guess it says. Does anyone know a work that just became non-copyrighted? Yeah. Mickey Mouse is still copyrighted. Yeah. Steamboat, did it? Oh, okay. So that's some new news. Some other new news is Winnie the Pooh. So Winnie the Pooh just became non-copyrighted. And actually, I just heard last week that somebody made a horror movie where Winnie the Pooh was a killer. And that won a whole bunch of like bad movie awards in 2023. So that's the kind of things that can happen to your copyrighted works if they are released CC0. Somebody can do anything they want with them. So you need to be a little bit careful about that. Next are MIT and BSD. These are very common software licenses. You'll see them on a lot of research projects. These have very few restrictions, other than maybe maintaining the copyright notice for BSD, but that's about it. You can do just about anything you want with it. Actually, I'm not sure if people know this, but the Mac operating system is based on an old BSD operating system where they took the code, they made it private, they forked it, made it private, and now it's the proprietary Mac operating system. So that's something you can do with an MIT or BSD license. There's also Apache and CC BY. Here you must acknowledge the owner of the original creators. So you need to say this person actually created this originally. Apache is also kind of interesting because they will give you a license to use that code and any patents that are associated with that code, unless you sue the company who released it. So just to give an example, let's say Google released their code under the Apache license, and that code implements transformers, and Google has a patent on transformers. So if you use kind of JAX or TensorFlow, a JAX or TensorFlow implementation of transformers that was created by Google, you're okay. You're safe to use that because they've released it under that license. But if you sue Google for anything related to intellectual property, Google could say, you can't use transformers anymore. And so like if OpenAI ever sues Google for intellectual property infringement, Google will say, okay, you can't use transformers or word embeddings. Good luck, OpenAI. So there's this interesting thing where all of these tech companies now are using patented things, a lot of it Apache licensed software. And so none of them can sue each other for patents. So patents have become basically mostly worthless in big tech. Moving on, there's also GPL in CC BY SA. These are licenses where if you use them, you need to reshare under that license. And so like if you create some software, it's GPL licensed and you build on it and build something new, you need to release it under the GPL license. So a lot of companies will not use will not use GPL software, because that would mean that if they incorporate it into their system, their whole system, like for example, Google, like all of Google would have to be GPL licensed and released. And I'm kind of simplifying these licenses. I'm just giving you the gist. CC by SA, and sorry, CC licenses are more for data. So MIT BSD, Apache, and GPL are more for software. CC Creative Commons licenses are for data. So for example, Wikipedia is CC by SA, I believe. Let me make sure that I'm not lying there. Yeah, CC by SA. And so that means that if you make any derivative work of Wikipedia, you need to share it the same way that Wikipedia is. So you need to give it the same license. There's also Creative Commons non-commercial licenses or software non-commercial licenses. These say you can't use them for commercial purposes. All the ones above you can use for commercial purposes. Once you start getting down here, this is often no longer called open source. So the open source initiative says anything with a restriction on the way that you can use it is no longer open source. And so that means if you say you can't use this for commercial purposes, or you can't use this in military systems, for example, which some language models say that nowadays, those are no longer called open source according to the open source initiative. So that's a thing to know about. Then separately, there are these licenses that a lot of people like Meta or Hugging Face come up with for their models recently. So the LLaMa license. How many people are using LLaMa in your projects? How many people read the license? So are you sure you can use it in your project? So you're probably in luck in your project if you're using it. The LLaMa license, you can read into it to see what it actually allows, but it has, the original LLaMa license has some interesting things. Number one, you cannot use LLaMa to train any language model that is not derived from LLaMa. So you can't generate data from LLaMa and train Mistral. That's not allowed according to the LLaMa license. Another thing is you can't use it for military purposes. So you can't use it in building a missile system or something like that. Hopefully none of you are doing that for your project. And you also need to get a license from Meta if you have something more than 300 million active users on your social network service. So if you're Google or X or Twitter or whatever else, you need to get a license from Meta before you can start using LLaMA. So basically, they created that license so their competitors don't take their language model and just use it for free. And then the final thing is no license. So like, let's say you have some code that you upload to GitHub and you don't put a license on your code. This means that you have only agreed to the GitHub licensing terms, which means that actually nobody can use your code. They can view it possibly, but they can't download it, use it. They can't they can't incorporate it into their own system. So actually, if you release research code, I would highly encourage you to use MIT or BSD or one of these permissive licenses so other people can use it and follow up and your code can be impactful. So this is an important thing to know about. There's obviously lots more to know about. So then my next question is, what is most of the text on the internet? The majority of the text on the internet falls into one of these categories. Any idea which one? So Wikipedia is CC by SA. What about most of the text on the internet? Yeah, it's not, maybe not no license, but all rights reserved. So basically you can't use it without having permission from the copyright holders. And so because of that, the idea of fair use becomes very important. This is a US specific thing, and the rules in other countries are different. They're not the same as the US, but in the US, we have rules about where you can use particular types of data. So the US fair use doctrine is basically that you can use copyrighted material in some cases. So as a gross simplification, quoting a small amount of material in like a textbook or slides or something like this is likely okay. There are going to be very few cases where this is not going to, where you're going to get in trouble for this. Another important judgment criteria for whether this is fair use is that it doesn't diminish the value of the original work. So if I quote something in my, like, let's say I quoted all of Harry Potter in a textbook, and then I sold my textbook for $3. Anybody could take my textbook and read all of Harry Potter for $3, and the money wouldn't go to J.K. Rowling. And that would not be fair use because it's diminishing the value of her work. Similarly, if I create a big corpus of books and I upload them to a site where anyone can browse them, that would also probably not be fair use because the authors would not get paid for it. Another judgment criterion is whether it's for non-commercial purposes or not. So like in universities, we're actually probably held to a more lenient standard of fair use if we're doing non-commercial research compared to a company that's doing it. So most data on the internet is copyrighted. So right now, most model training, not all model training, but most model training is done assuming fair use, which means that training an AI model on copyrighted data is, number one, it cannot reproduce the material easily. So it's, instead of quoting material directly, it's kind of combining the material together to create a new thing. They're saying it doesn't diminish the commercial value of the original data. And then the non-commercial purposes is maybe a secondary concern since the first two hold. But there are lawsuits about this. And so this is a clip from the New York Times where the New York Times is suing OpenAI and Microsoft over them training on New York Times articles. And they do a lot of things, like they demonstrate that you can get GPT-4 to reproduce New York Times articles. And they also argue that people are using this GPT-4 as a source of news instead of going to the New York Times site. So they're losing money from advertising and like other things like that. Another example is GitHub Copilot was sued by people who uploaded software to GitHub and said that basically GitHub didn't have the right to use it to profit from it and diminish their, their money. So notably, on this slide, I'm using fair use. I don't know if you've noticed. Like I copy pasted an image from somebody's website and used it here. That's copyrighted material, but I'm using it because I'm quoting a small amount of material and I'm not diminishing their commercial values. So like fair use is very ubiquitous. It's very important. So we can do things like this, but also it's currently under dispute with respect to models. So then another question is, why restrict model access? Why do we, number one, make models closed? Number two, maybe not even describe what we did in our models. And I think there's three main reasons. The first reason is commercial concerns. And so they want to make money from the models. So OpenAI makes money from the OpenAI API. Google makes money from the Gemini API. And Anthropic makes money from the Claude API. These are all models that I'm going to talk about. Number two, safety. I think there are very legitimate concerns where if you release strong models, people might use them for bad things. So, creating fake content online or doing spear phishing attacks against people and trying to, scam them out of money or things like that. So I think there are legitimate concerns about this. And then the final one is legal liability. So training models on copyrighted data is a legal gray area, as I just mentioned. So they don't want to say what data they trained on, because if they say what data they trained on, then they might get sued. So these are the three main concerns. So anyway, this is a preface, and then I want to go into like the actual models. But are there any questions about this? So if any of you are working at a company or starting a company, thinking about working at a company or starting a company, this is something you should be aware of. You should also be aware of the fact that, OpenAI has been doing sketchy things for a long time, and look where they are. So, it's like, this is very much a legal gray area, and people are moving through that gray area. But anyway, it's worth knowing that. So next I'm going to talk about open models. So first, a bird's eye view. I'm going to talk about 5 different models, and I picked them for a reason. The first 2 are because they're open source and fully reproducible, namely Pythia and OLMo. And the reason why I want to talk about these is we know everything about them, including what data they were trained on, what their training procedures are. You can download all the stuff, so you can kind of know exactly what goes into making a strong model. Pythia actually has many sizes and checkpoints, which is pretty interesting, and OLMo is maybe the strongest reproducible model at the moment. Then we have open weights models, and these are models that aren't fully open. They don't disclose everything. They don't release their training data or code. But I'm going to talk about LLaMa 2, which is the most popular. It's also heavily safety tuned. Mistral and Mixtral, which is a strong and fast model. It's somewhat multilingual. And also Qwen, which is a very strong model. It's more multilingual, and specifically, it's good in English and Chinese because it was trained on lots of that. So first going into Pythia, for each of them, I'm going to give an overview and then talk about some interesting points about them. So Pythia was created by Eleuther AI. Eleuther AI is one of the first kind of open source AI organizations. They've created a huge number of really useful things, including training code, models, training data sets, and also evaluation that's used pretty widely. The goal of Pythia was basically joint understanding of model training dynamics and scaling. And so from that point of view, they released 8 model sizes from 70 million parameters to 12 billion parameters. For each model size, they have 154 checkpoints throughout the training process. So they basically trained on 300 billion parameter tokens and did checkpoints, periodically during that training process. So you can do interesting things like say, how quickly do small models learn things? How quickly do large models learn things and other stuff like that? In terms of the architecture, as I mentioned at the very beginning, the architectures are actually very similar between them. So it's almost easier to point out their differences than their similarities. Actually, one thing that's not on the slide is I mainly focused on the 7 billion models because almost everybody trains a 7 billion model. It's just kind of like one of the standard sizes. It's the smallest size of LLaMa. It's one of the largest. It's the largest size of OLMo and one of the largest sizes of Pythia. 7 billion models are generally 4096 wide, 32 deep, 32 attention heads, and their hidden layer size is about like 8/3 of the size of this. And this is kind of the standard LLaMa 7B architecture. As you scale up to larger sizes, you just increase the number of layers, you increase the width and other things like that. So that's very standard. The other standard is everybody uses a transformer. Everybody uses pre-layer norm, like I talked about before. Everybody uses rope embeddings. Almost everybody uses a swig glue activation. So this is just kind of the standard recipe that almost everybody uses. Where things start to change a little bit between the architectures, which arguably might not be very important, is how long is the context length. So Pythia is 2K context compared to LLaMa 2's 4K context. Actually, LLaMa 1 is 1K context. So LLaMa 1 is 2K context and LLaMa 2 is 4K context. Another thing is, where do they put biases in the model? Most people don't use biases anywhere, but sometimes they put them in various places. The other thing is the variety of layer norm that people use. And Pythia was using standard parametric layer norm, but gradually people are stepping back from that and they're using like RMS norm or even non-parametric layer norms. So small architecture differences, but almost everybody uses something pretty similar. The data. This was trained on 300 billion tokens of the pile, which is on the next slide. But one interesting thing is that they also did a deduplicated training run on 277 billions of the token. 207 billion tokens. And the idea is that they they wanted to test how important it is to duplicate, how much do you gain by deduplicating in terms of training efficiency. And they have different learning rates for different model sizes. The 7B model is 1.2 times e to the minus 4. In contrast, LLaMa is 3 times e to the minus 4. So this is a potentially big change because the learning rate is actually half the size here. Is the batch size, they use 2 million tokens, and actually LLaMa 2 uses 4 million tokens for the batch size. So there are some small differences there. So next, I'd like to talk about the pile. This is kind of the original open data set for training large language models. That being said, it's a really nice data set made out of lots of different types of data. And namely, it's trained on academic data. So that includes things like PubMed, Archive, Free Law, the US Patent Office, other stuff like that. It's also trained on internet data. So this is data that's just scraped from random parts of the internet, but also Stack Exchange and Wikipedia. It also has some prose. So these are like book data sets. It has some code data sets, and it has some like subtitle/dialogue data sets in it. So this overall is 800 gigabytes, or about 300 billion tokens, according to it. So some of the findings from the Pythia paper, in addition to just being like one of the original strong open language models, is they have some interesting analysis into model memorization and how quickly models learn based on the number of tokens that you show them. And this graph is maybe a little bit hard to see from the back, so I'll interpret it. The left side is one of their smaller models, 160 million. The right side is their biggest model, 12 billion. The different lines here are different steps of the training process. So like 13,000 steps, 39,000 steps, and et cetera, et cetera. And the x-axis here is the frequency of a fact in the training data. And the y-axis is question answering accuracy about that fact. And so what this is basically showing is as you scale up the model, the larger models learn faster up to a point. So like right here, you see the 2.8 billion model is about the same as the 12 billion model at earlier parts of the training process. But as you get later in the training process, the 12 billion model is like memorizing and being able to recall more facts. So like right at the very beginning, you need to scale up till about 2.8 billion to learn efficiently. But at the end, this model is like better further on. So this is really nice. All of these checkpoints, all of this data is open. They even made the data loader so it's reproducible. So you can look at the actual data that the model was trained on at each of the checkpoints. So if you want to do this sort of analysis, this is a good set of models to look at. Another thing that they did is they actually did interventions on the data. So they tried to intervene on the data to modify it because male or masculine pronouns were much more frequent than feminine pronouns in the data. So they intervened on the data to try to balance out the distribution of masculine and feminine pronouns, and demonstrated that the model became less biased towards generating masculine pronouns later. So they also were able to do those sorts of intervention studies. Any questions about Pythia? Or? Okay. Next, I want to go to OLMo. So OLMo is a more recent model. Pythia, I think, came out around a year ago. OLMo is very recent, about a month ago. And this was created by AI2, the Allen Institute for AI. One thing you'll notice is the two completely open models that I'm talking about both came from nonprofit organizations. So Eleuther is nonprofit, AI2 is nonprofit. So they're maybe a little bit less worried about people trying to sue them for lots of money for fair use violations. So that's the cynical point of view. The non-cynical point of view is they have nothing to profit by creating a better model, by having other people create a better model. So they're willing to do this for open and good science. their goal is better science of state-of-the-art LMs, and some of the unique features are top performance of a fully documented model, and they also have instruction tuning models, et cetera. Looking at the parameters, basically similar to LLaMa, the one big difference is they're using non-parametric layer norm instead of RMS norm. So this is basically layer norm with no parameters whatsoever. They didn't super clearly justify why they decided to do this. One difference from Pythia, this was actually trained on 2.46 trillion tokens. So compare this to Pythia, which was trained on 300 billion tokens. And so they basically trained it for a lot longer. They trained it on something called the DOLMA corpus, which they also created at AI2. Actually, I think this might be wrong. So just ignore that. That was a copy-paste mistake from Pythia. So they always use 3e to the -4, which is a learning rate, which is the same as LLaMa. And the batch size is 4 million tokens, which is also the same as LLaMa. So the DOLMA corpus that they created is actually pretty similar to the pile, but it's a larger corpus. It's 3 trillion tokens. This is also fully open, so you can download it from Hugging Face if you could find some disk to put 3 trillion tokens on. Another thing is that they have a data processing pipeline of language filtering, quality filtering, content filtering, deduplication, multi-source mixing, and tokenization. And so the nice thing about this is a lot of this stuff is usually proprietary for most language modeling creators. So if you want to see all of the data processing pipeline that goes into training a model, this is a pretty good example of that. The document types that are included are the common crawl. And so the common crawl is just data crawled from the internet. It's about 2.2 trillion tokens. They also have the stack, which is lots of code, about 400 billion tokens of code. C4, which is also web data, Reddit, STEM papers, books, and Wikipedia encyclopedia text. So you can see that it has a fairly large amount of coverage, although mostly in English. So some findings from OLMo that I found interesting. Number one, it has competitive average performance. So as I mentioned, I think this is the first fully open and documented language model on the 7 billion range that is competitive with all the other kind of less open models in this range. So for example, LLaMa 2 is 70.5 average on all of the data sets that they're evaluating on. Falcon is 70.3. MPT is 69.8, and almost 69.3. So it's not a slouch with respect to accuracy compared to Pythia, which had 63. Much of the issue with Pythia could just be that they didn't train for long enough. And some evidence of this is where they measured performance constantly as they trained for longer. So the left side is training on 500 billion tokens, which is already more than what Pythia trained on. The right side is 2.4 or 2.5 trillion tokens. And you can see, interestingly, that the numbers are just continuing to increase as they train for longer. So it seems that training for longer and longer just kind of helps. One question is whether they're overfitting to the data set. Is any of the test data included in their training data here? They did do deduplication to some extent to try to remove the test data. So I think it's quite probable that these are real gains, and if they train for longer, they might get an even better model. But I'm not, 100% sure about that. Cool. Yeah, one other thing that I noticed, which might be a little bit interesting, is all of these that I didn't mention here is all of these have a learning rate schedule. And typically they have a learning rate schedule where they do the standard warm up where they increase and then they decrease, but they stop decreasing at a floor. And usually that floor is about 1/10 the size of the original learning rate. So if they start out 3e to the -4, they'll decrease it, but only to 3e to the -2, and then they'll continue training. So that might be another good thing to know about. Cool. Any questions about this? Okay. So now I'll get into LLaMa 2. And LLaMa 2, is a model that probably most people have heard about. It was created by Meta. It's one of the strongest open language models now, although arguably there might be stronger open language models. And the goal is a strong and safe OpenLM, and they have base and chat versions of it. And some unique features are, I think this is the open model with the strongest safety safeguards. So it is, if I were to pick one model that I wanted to use in an actual system that was directly conversing with users, I would probably pick this one over something like Mistral. Even though Mistral shows superior performance some of the time, it might say things that you don't want it to be saying to like users. So I think that's one of the nice things about Llama. So I've been comparing everything else to it, so that's pretty normal. One thing about the data is the data is not open. They didn't say what data they trained on for reasons that I talked about before. What they did say is it was trained on public sources, upsampling the most factual sources. So that's what they said. The LLaMa 1 paper has more information. And so I'll talk about what they did in the LLaMa 1 paper, and we can maybe extrapolate that they did something similar in the LLaMa 2 paper. And then the total training amount is 2 trillion tokens. So that's actually less than LLaMa. So if we look at the LLaMa 1 training data, it looks a little bit like, it looks very much like the OLMo training data. It's Common Crawl, C4, GitHub, Wikipedia, books, archive, Stack Exchange. And one thing you'll notice is that they upsampled Wikipedia and books and downsampled GitHub, compared to the amount of data that they actually had. And so they did 2.4 epochs over Wikipedia, 2.2 epochs over books, and only 1 epoch over like the standard web data in archive and Stack Exchange, and 0.6 epochs over the GitHub data that they had. So obviously they thought that this Wikipedia and books data was more valuable for some reason, and they really wanted the model to learn well out of it. So I think when they say that they upsampled factual data, I'm assuming that that's also what they did in LLaMa 2. So the next thing yeah. What does it mean to have like? Yeah, actually, that's a really good question. So why are epochs not integer values? There's actually no reason at all that you should do, an integer value of epochs. You can always save out a checkpoint every, 10,000 steps or something. So I'd actually encourage people to get away from saving out checkpoints every epoch, because that kind of discourages you from making your training data larger. Because if you make your training data larger, you'll think, oh, training takes forever. Because it takes forever to use an epoch, but in reality, you can just save out, periodically and keep the checkpoints from earlier. So many language models don't train on all the data on the web because it would just be too expensive to do so, despite the fact that they have all the data on the web. But very good question, though. That's an important point. Okay, so now I'd like to talk a little bit about the safety tuning that goes into the LLaMa models. I might talk a little bit more about this later, but I think I'll talk about it now. Basically, the LLaMa 2 developers put a lot of effort into training the model to be safe because, they're a big company and they don't want any PR disasters. And also, they want an actual safe model that they can use and deploy in their products. So I think they have the dual motivation there. The first thing that they did was they collected lots of data for reward modeling. And reward modeling, what they're calling reward modeling is basically preference modeling. So they have, multiple outputs where the 2 outputs are somehow ranked for preferences. And I talked about this when I was talking about DPO and the reinforcement learning class, for example. A lot of these actually exist. So there's like the Anthropic helpful and harmless data sets, these OpenAI data sets from WebGPT, Stack Exchange, on Stack Exchange, they have helpful answers and not helpful answers. So ones that you give thumbs up and thumbs down to. And the Stanford Human Preferences data set, I forget what S stands for. Human Preferences data set. Basically, this is where they tried to find Reddit posts, I think Reddit posts that got more upvotes despite the fact that they were posted later than a previous one. So the idea is like usually the first posts get more upvotes. So if you get more upvotes for a later post, that indicates that you're probably more valuable than the earlier post. So kind of clever way of creating data. I'm actually not sure what the synthetic GPT was. I didn't look at that. And then separately from that, Meta collected a very large amount of internal data that they didn't release for tuning LLaMa. And they did this through various iterations. So basically what they did is they created a first version of the model. They let it loose on users. They also did some data collection with people who were actually trying to break the model and getting it to say bad things. They collected preference data from these people, and then they iterated over and over again to collect more and more of this data on various versions of the model. So as the model gets better, it's going to be harder to collect this data, but they want to try to improve the current model that they have. So the next step that they did was they trained a model to follow these preferences. And so they trained a model that basically can predict human preference given two language model outputs. And this is a hard problem, right? Because these are language model outputs. And the language model thought it was a good output regardless, because otherwise it wouldn't be sampling. And so you need to distinguish between two very fluent looking outputs where one is preferred and one is not preferred. So even kind of strong models like, oh, by the way, there are some open reward models. Like this Open Assistant reward model is publicly available and you can just go and download it if you want it. But this, if you evaluate it on this Anthropic helpful and harmless data set, this gets about 67 or 68 accuracy. But if you evaluate it on this like Open Assistant data set, if you evaluate the public models, including GPT-4, on the Meta data set, actually it's pretty hard for to distinguish between the things. And here they're evaluating both helpful and harmless, or helpful and safety. And the reason why is because like it's very easy to create a very safe but not helpful at all model by saying I don't know all the time. It's relatively easy to create a helpful model that's very unsafe, like it will do anything you want. And so they want to balance between the two, and they evaluate them separately. They also created two different separate reward models. So they created one reward model to distinguish safety and another reward model to distinguish helpfulness. And they use these separately to train the model. And you can see that the helpfulness model does a lot better on discriminating between helpful things, and the safety model does a lot better on discriminating, or does a little better on discriminating between safe and unsafe things. Actually, I didn't include this in the slides, but they also have an interesting graph that demonstrates how good the reward models are based on their size. And it turns out that this is a place where it's really, really important to use a large and powerful language model to determine your reward, because they demonstrate that the 70 billion parameter model that they used is actually far better than the smaller models that they used at predicting this reward. So this is a graph of their incremental training process for safety tuning. And you can see they have their first supervised fine-tuned model. This is with no like RL or anything like this. This is a second model. And it improves a lot with respect to helpfulness. And then they do more and more RLHF, where they start with the like supervised fine-tuned model and gradually do add more reward data, train with a better reward model. and get to the end where they finally have the best model and I believe this is the one that they actually released. So you can see that they really put a lot of effort into making this model, safe. And that's one of the main points of the paper that they had here. Another interesting part of the LLaMa 2 paper is how they got it to follow chat instructions. And so I think you're all familiar from the class where I talked about prompting, where basically they prompt the language model using a system message and a user message and an assistant message. And so the characteristic of the system message is this is something that you want to be obeyed throughout the entire conversation, right? And so in order to get this obeyed throughout the entire conversation, you need a model that's good at paying particular attention to the system message. In this example, I'm saying write in only emojis. So no matter how long this conversation gets, you want your model to continue writing in emojis, and models don't do this spontaneously. So what they did here, and I'm 90%, 95% certain that my interpretation of the paper is correct. The paper is a little bit hard to understand with respect to this, but what I think they do is they take the system message and then they have a data generation step where they basically ask an existing model to write in only emojis and then say hello. And then the model generates something. And then they say again, write in only emojis, how are you doing? And then they generate it again. And because this is so close in the context, the assistant basically will continue paying attention to these directions. And then after that, now you have a data set that you can train your model on. You can train your model on this generated data set that looks like write in only emojis, say hello, how are you doing, and stuff like this. And they try this with a whole bunch of rules. It's like write as if you're explaining to a 5-year-old, or write in a very polite manner, write in a very informal manner, and stuff like that. So they generate a whole bunch of this synthetic data. And in doing this, they basically are able to train the model to pay very close attention to the system message because it needs to do so in order to do better. So yeah, these are kind of the unique characteristics from LLaMa 2. I'd love to tell you more about its training data and all that other stuff, but they didn't tell us like what they did with respect to that. So we'll just have to infer from LLaMa. Cool. Any questions about this? Okay, I'll go. So next I want to go into Mistral and Mixtral. This is going to be a little bit short because I've kind of covered some of this stuff already, and also they didn't tell you very much about the training process. Basically, it was created by Mistral AI, the company, and it's a strong and somewhat multilingual open language model. It has some unique features like speed optimizations, including grouped query attention and mixture of experts. It makes, unlike the other ones, it makes some actual architectural modifications, including sliding window attention and mixture of experts. And I have actually talked about both of them, so I'll just very briefly go through them here. The data, as far as I could tell, was not disclosed very completely, but one important thing is it includes English and European languages, so at least theoretically it should be better than LLaMa at this. One interesting thing about LLaMa is LLaMa, if I remember correctly, the actual numbers are in the paper, but it's something like 85% English, 8% code, and then like 0.3% other languages. Like starting in all of the other languages, it's like 0.3%. So it's not very multilingual at all. And they were really only aiming to create a good English model. Also, the training details were not disclosed here. Like I wasn't able to find the batch size as far as I know. So Mistral uses sliding window attention. Vanilla attention, basically, you always attend to all of the previous things in the sequence. What Mistral does is it attends to the previous n examples where n is equal to 4096. And because of this, what this means is you can attend 4096 back, And then in the next layer, you can attend 4096 back, then you can attend 4096 back. So basically, as many layers as you have times 4096, you can attend that many tokens back for a minimal training penalty, because still the length of attention for any particular token is the same. So that's one feature. Oh, and then, yeah, sorry. The other feature is Mixtral is using a mixture of experts, like we talked about in the previous time. So despite these are very strong models. They're generally stronger than LLaMa at a lot of things. And Mixtral is actually a lot faster and easier to deploy than LLaMa 7DB. It's smaller. It only has 45 billion parameters. So it's definitely a good choice if you want to use it on the train. Yeah. So the sliding window yeah, so it's attending to 4096 tokens. So the context size, typically, like let's say you have a block of 4096 tokens here. Typically, that means that the first token attends to 0 tokens, the second token attends to 1 token, and the third token attends to 2 tokens. Here, this is maybe a little bit misleading, I guess, but if your context length is 4096, you actually get a block of twice that size. You get a block of 8192 tokens. And so the first one attends to all of the previous ones. So the first, so the 4097 token attends back to all the tokens from 2 to, sorry, either 1 to 4096 or 2 to 30. And so because of that, you move to the very end, then you have the 8192 token. That's attending from like 4096 to 1. And so like every token is always attending to the previous one, and that allows you to kind of attend to things in the previous block. No, it's big. So that allows them to attend to very large amounts of. Cool. So the next one I'd like to talk about is Qwen. This is one that in the US, at least, people maybe pay a little bit less attention to. But it was created by Alibaba, and it's a strong multilingual model, especially English and Chinese, but even in other languages as well. And one of its defining characteristics, other than just being a strong model overall, is that it has a large vocabulary for multilingual support and strong performance. It comes in several sizes. I believe there's a 7B version, and then there's also like a large, like 70-ish B version, 72B, I think. And it's using very standard architecture things. The only small difference it has is it has a bias in the attention layer, which doesn't exist in LLaMa. An important thing is it's actually trained on multilingual data, and they use a large vocabulary. They use a vocabulary of 150K in contrast to LLaMa's 32K. And that allows it to handle multilingual data relatively well. And we have the 3 similar, training regimes. So overall, it's not very different from LLaMa. What might be different is data engineering. And actually, I expect the data engineering part is a bit different because overall, it's a bit stronger than LLaMa 2. And I think that has to do with data in various areas. One interesting piece from the paper that they have is if we think all the way back to when we talked about subword models and word tokenization, well, remember that subword models split up the input, and they split up the input so that frequent tokens get longer outputs and infrequent tokens get shorter outputs. So one of the problems, as I mentioned a long time ago when we covered this topic, is this causes issues if you're doing multilingual things, because if you have very little multilingual data in your training data for the subword tokenization model, it will end up splitting all of the words into basically characters or even bytes. So what this shows here is this is comparing the amount of subword tokenization that happens according to each of the LLM's tokenizers with another explicitly multilingual model, XLMR. So XLMR is kind of their baseline here with respect to how much it tokenizes each language. And on the very left, we have LLaMa. And so what we can see is that LLaMa tokenizes Thai 3.7 times as much as XLMR does. So it's basically splitting Thai up into little tiny bits, which makes it very expensive and ineffective to process. Let's find some other languages that we care about. We have Hebrew, Arabic, Korean, Japanese, Chinese. So all of these you can see are split up pretty into many different chunks by LLaMa. And then we have a few other language models in the middle, and then we have Qwen on the right side. And what we can see is basically it's pretty comparable to XLMR, maybe a little bit more than XLMR, but pretty comparable to XLMR on many languages. And then on code, it actually splits up code much less. So we can see that, its tokenizer is heavily multilingual. Another thing I'd like to point out is I'm focusing on this particular language model for a number of reasons. The first one is multilinguality, and I like multilinguality. I hope other people like multilinguality too. But another motivation is just it has quite strong performance, and it's topping the leaderboards in several different places. So if we look at the OpenLLM leaderboard, at least recently, this was a fine-tuned model by Abacus AI, which was originally based on Qwen. So you can see that this is like a strong foundation model that lots of people are using for fine-tuning things. So I would definitely encourage you to take a look at that too. Of course, there's many different models that I didn't cover, because if I covered all of the general purpose models, then we'd be here all day, but that's a first start. So next I want to go into other kind of special purpose models, but are there any questions about the things I covered so far? Cool, okay. So next I'd like to go into other models. First is code models. So code models are models that were specifically trained on code. Actually, right now, every model is a code model. Like nobody pre-trains a large language model and is serious about it and doesn't train on code, because generating code is a huge use case. And also some work has demonstrated that training on code seems to improve reasoning abilities of language models as well. But these models were very heavily trained on code. So we have StarCoder 2. This is a very recent entry. This is a fully open model. So you can see the data it was trained on. All of the training details are released and other stuff like that. So this is kind of in the Pythia, Pythia OLMo category, but it's actually a very strong model, very good model. So it's a good one to know about. Separately, there's CodeLaMa by Meta, which is a code adaptation of Llama. And it also gets quite good performance. There's also another model called DeepSeek Coder. I would say all three of these are topping some variety of leaderboard, where DeepSeek maybe is topping a few more leaderboards than the other ones are, but all of them are very competitive and might be the best in class for code things. I'm not talking very much about these because we're going to have a class on code generation and code related things later. So I'm not going to go into a lot of detail here. Another thing is about math models. And so like one interesting thing is large language models are not particularly good at math. So there are quite a few models that were trained specifically for math. The first one is LLaMa. Yes, that is a pun for like lemma from math. I'm not responsible for it, but I thought it was kind of funny anyway. This was by Eleuther AI. So because this was by Eleuther, again, this is a fully open model. All the data is open. Everything is known about it. Also, our very own Sean Wellick was one of the contributors to it. So if you want to know more about lemma, you can go bother Sean. So that's another thing that I should mention. Another thing is DeepSeek, who made the DeepSeek coder model, has also created a very strong math model that's competitive with GPT-4 on a lot of math things. Basically, the way they did this was they did this by training a classifier to try to identify data on the web that is related to math and scraping all of that data and fine-tuning on it. So you can get gold standard data from like Proofpile and a whole bunch of other sources. And so they trained a like math or not math classifier and harvested a lot of math related data. Yeah. It's mostly data sets. I actually might be talking a little bit more about these in the reasoning class, and I did a lot of prep to create these slides and actually ran out of time to do the math stuff, so I might talk about it later. But I don't think they're really doing a lot of things. Like you could think of obvious things like doing RLHF based on like whether it gets the answer right or not in the end. As far as I know, that's not a big ingredient here, but I'll be more sure of that when we talk about it later. Cool. And a final one, it's not a synths model, it's a science model. Sorry for the typo. But this model, Galactica, was a model for science that was trained by Meta. Does anyone remember this model, or was anybody around when this model came out? No? There was a big PR disaster for Meta when they released this model because they said, this is a great model for math, use it in writing your science paper. Sorry, this is a great model for science. Try using it in your science papers. And this came out about 2 years ago. And 2 years ago, language models hallucinated all the time and came up with false scientific facts and stuff. And so basically, a lot of people kind of bashed this model. In my mind, kind of unfairly, because they actually have a lot of really interesting things in this paper. One interesting thing in this paper is they tried to create a general purpose model for science that's able to understand not only text, but also various modalities of scientific data. And so that includes text, it includes latex, equations, it includes code, but it also included things like molecular structures and like collagens and DNA and stuff like this. So they tried to like model biology and other things like this as well. So I think it's really kind of too bad that this model got a bad rap, because I really like the work that went into it, and I hope we'll see more of this, because language models for science is a really big topic that a lot of people are thinking about. Cool. One thing I didn't talk about is multimodal models, but I hope to talk about multimodal models in a future class. So I'll talk more about that soon. The next thing is closed models. So closed models, we don't know a whole lot about them. Most of what we know about them in their training data and other things like that is conjecture. So the standard format for releasing in a closed model, or not releasing, but publicizing a closed model, is people will write a blog post and they'll write a paper. And generally what the paper does is it only talks about evaluation. It only talks about like how good the model is on various things, how safe it is, how they put a lot of effort into red teaming the model so that it doesn't do bad things and stuff like that. And it tells you nothing about how they actually built the model. So mostly like what I can talk about are capabilities as opposed to like what actually went into the model. So there's GPT-4. GPT-4, I think everybody knows, it's kind of the de facto standard strong language model. It used to be the only strong language model. Like it used to be on its own the strongest language model, and there were no real competitors to GPT-4 from that point of view. I think still, if I wanted a strong language model for just something that I'm going to do randomly, I still trust GPT-4 more than anything else to give me a really good answer. But there are now other competitors that I'd like to talk about. So GPT-4 anyway, it powers the pro version of ChatGPT. It was tuned to be good as a chat-based assistant. It accepts image inputs, and it supports calling external tools through a function calling interface. I think people are generally familiar with this, but just in case you're not, I'd like to show a few things that I like to do. So let me. So I'll just randomly grab one of my papers from archive, my most recent paper, and I can copy paste this. And turn this into JSON format. And I drop it in here. And so this is an exhibit of its like multimodal abilities, because I can throw in a table, and it basically turns it into JSON format for me. So I actually turned a fair amount of data that I created in creating these slides into JSON format, so I can save it later for whatever I want it for. And I did it through this. So this is an example of the multimodal abilities. Can also tell you about images and stuff like that. There was a famous article written by Gary Marcus that said deep learning is hitting a wall. It basically was written 2 years ago. And Gary Marcus was saying deep learning is not the way for the future. We're going to need things other than deep learning in order to, be able to make progress. And whether you believe that is true or not, I will let you to your own opinion. But I could also say create a picture of deep learning breaking through a brick wall, and it can generate images for you. Of course, if you ever do a live demo, even if it's a live demo of OpenAI's product that 1 million people use, it will break when you try to do it. So this is another thing that it can do. So there we have a picture of deep learning breaking through a brick wall, and it can, generate images and stuff. So these are like the kinds of things that I now expect. So it's not just like reasoning ability and other stuff like that. It's also multimodality, being able to generate code. Another thing that's kind of nice is make a histogram of these numbers. 1, 2, 1, 2, 4. So it can do code generation and display the results for you. There are efforts to make open source language models be able to do these things. And in order to do this, you need multimodality. You need also the ability to use tools. So actually, the way that this worked here is very different than the way that this worked. So this is actually using a image input into GPT-4. So what it's doing is it's encoding the image and then feeding it in as tokens into GPT-4. what this is doing here is this is rather calling a tool. This is calling Dolly 3 as a tool, and it's providing the caption to Dolly 3. You can even see maybe the caption that was provided to Dolly 3. You previously were able to do that by maybe downloading. Yeah, so you can see the caption, which was a visual metaphor of deep learning is a powerful force breaking through a brick wall, or something like that. And so GPT-4 basically what it did is it said it wanted to call a tool, and then it provided the caption, and then it called a completely separate tool as an API in order to generate the image. So yeah, the final. Well, I managed to break ChatGPT. That's no small accomplishment. But anyway, these are some of the things that that these systems can do. And because OpenAI has kind of become a standard that a lot of people want to compete with, also, I would say Gemini and Claude are maybe the two models that can compete with GPT-4 in terms of accuracy. Gemini is a much newer model by Google that comes in two varieties, Gemini Pro and Gemini Ultra. One interesting thing about Gemini Pro is that it supports very long inputs, 1 to 10 million tokens. It also supports image and video inputs and image outputs. I actually put a video into it recently, and the video recognition capabilities are pretty nice. So you can try that out if you want. And finally, there's Claude. Claude 3, it supports a context window of up to 200K, also allows for processing images, and overall has strong results competitive with GPT-4. So if you're looking for models to use to try out that are closed models, you can definitely use these. Another thing I'm really excited about is how can we get like open models to demonstrate some of the interesting capabilities that we see in closed models, so everybody can benefit and everybody knows the recipes to make models like this. So I think that's mostly all I have for today. Another thing that is kind of neat is I just found this a little while ago. But there is this interface called the God mode that allows you to put all of the chat apps next to each other and write the same chat query into them and get the result from all of them. So you can actually compare all of them in kind of an interactive setting. So if you want to look at especially all of the closed models, open models, it's not too hard to do it yourself, but if you want to try all of the closed models together, you can do that and like log into all of your accounts and then press go on a query and see how they all respond. So that might be a good way to compare all of the models kind of qualitatively as opposed to quantitatively. Cool. That's all I have for today. I don't know, are there any questions or discussion or things like this? Yeah. So a systematic way, the first thing you can do is look at the benchmark results that have been published. But actually, I would like to give a caveat about this, which is so these are the benchmarking results for the Gemini paper. And they have a table here, and basically what they kind of obviously to me wanted to demonstrate is that Gemini was the best model out of all the models. And so they have Gemini Pro and Gemini Ultra, and they put Gemini Pro Ultra against GPT-4 and Gemini Pro against GPT 3.5 because they're, you know, comparable models. And they're, yeah, because they're comparable models, basically. And on things like, and they demonstrate that basically they're better in all of these situations. However, there's a few details. The first detail is that the method that they're using to prompt the model is different here. So we have like 94.4 versus 92, but the method they're using to prompt the model is different. They're sampling 32 and then basically getting the best from 32. And then another thing is, if we look at this human eval performance here, they reported their human eval performance, then they pulled the number from the original GPT-4 paper and compared to the number from the GPT-4 paper. But all of these, you know, APIs are constantly changing. They're getting better and better. So we went, I was very excited when Gemini first came out, and we actually wrote a paper where we tried to look deeper into the performance. And what we actually found is comparing Gemini Pro and GPT 3.5 Turbo, which should be comparable, we found that actually GPT 3.5 Turbo did a little bit better in most cases, although not all cases. And one of the things we noticed in particular is like human eval, GPT 3.5 had gotten like much better over the course of like the time between the original paper was reported. It had gone up by almost 30 points. And also in a few cases, we had like a little bit of trouble reproducing the Gemini Pro results just because they had like safety filters and other stuff like that that we had to get around before we got the results. So it's not necessarily the case that you can completely take the results on face value. Actually, as a first step, I would suggest just trying to chat with the model, which is also why I introduced the like quote unquote God mode like browser, because like you can kind of tell when something's way better than another one just by the responses it gives. Separately, if you want to do it much more systematically, there are really nice tools for evaluation. I think I might have talked about this before, but if I haven't, then you should definitely take a look at this. There's the Eleuther evaluation harness. And the Eleuther evaluation harness makes it really easy to evaluate, for example, Hugging Face models against many different tasks. So you can just pick which task you want to evaluate against, pick the model name and go, and you can get evaluation results. That won't necessarily work for closed models. But if you look for Eleuther language model evaluation harness, that's maybe the easiest way to run evaluations yourself for LLMs. Cool. Okay. So we're at time now, but I'd be happy to answer a few questions if anybody else has any. So thank you.